Hi, welcome back. In this lecture, I would like to give you a brief history of quantum computing. By no means this is a complete history of quantum computing, but I just want to give you some little bit of context about quantum computing and all the topics that we're going to look at in the course. Probably the first paper that is relating quantum physics and computation is a paper written in 1979 by Paul Benioff, who is a scientist at the Argonne National Lab. The title of the paper is The Computer as a Physical System. In this paper, Paul Benioff put in relation the quantum physics with computation. In particular, he says that computation is a physical process. It can be described by a pure state, that can be a quantum state, that is evolving under the action of a given Hamiltonian. Hamiltonian is a mathematical operator that describes physically the total energy of the system. The main step towards quantum computing in this paper is to say that the quantum computing system can be a Turing machine and therefore can be used for computation. Paul Benioff suggested the possibility of actually building a computing system that relies on quantum physics. Probably the major and most famous player in quantum computing is Richard Feynman, that in 1981, working at the Caltech, he prepared a lecture that is entitled Simulating Physics with Computers, that then will be presented at one of the major conferences that open up to the thinking about quantum computation and quantum physics for computation that was organized by MIT and IBM. The conference was at MIT. Interesting enough, Paul Benioff was also a speaker at the conference. So what Richard Feynman argues is that a classical system cannot be adequately represented a quantum mechanical system because it's not a quantum system. He argues that since fundamentally nature is quantum, has the most important description of nature is a quantum description, then we also need the quantum computer to describe the quantum computation. This is probably the most famous quote that is motivating all the development of the quantum computing theory and technology. So the quote is, "Nature is not classical, damn it, and if you want to make a simulation of nature, you better make it quantum mechanical." And my goal is a wonderful problem because it doesn't look so easy. So at this point, the major motivation is there, but features of quantum computer are unclear and unclear how to build the machine. So since the 1980s, basically there's been quite a lot of work thinking how to develop a quantum computing system. So probably the most important issue to solve at the beginning of quantum computing was to develop a computing system that model exactly non-physical laws, so both classical and quantum. And one of the major characteristics of a quantum system is that they are reversible. That means that we can go back and forth time. So it turns out that the classical gates like AND and NAND are not actually reversible. So this cannot be really quantum gates. What it means that AND and quantum and NANDs are not reversible? Well, it means that if we do AND operation operating on two variables, and when we get results of this logical operation, we cannot go back from results back to the original variables. So quantum computing, we will see later on in the course, requires to be reversible. So classical gates like AND and NAND are not reversible, and therefore they won't find any direct equivalence in quantum computing. A major fundamental work has been done by Fredrickson and Toffoli from MIT that theorize and develop universal reversible. So reversible here is the important part, gates. Some of these gates are actually implemented in 2016. We will see the Toffoli gate, we will see the control NOT gate that actually are reversible gate. So these reversible gates are the building blocks of quantum computers. And you can look at the paper by Fredrickson and Toffoli online here, will be also posted on Canva. Among the most famous players in quantum computing and in theoretical computing science, when it comes to quantum computing, there is Deutsch, that suggests a more comprehensive theoretical framework for quantum computing. And his seminal work in 1985 paper, with the title Quantum Theory, the Charge Turing Principle and the Universal Quantum Computer, is a fundamental work that first describes how a quantum algorithm would look like, and also anticipates that one day will become technological, possible to build a quantum computer. So nowadays we are in the period where actually this is actually happening. So that was a very nice prediction. And then, most importantly, he devised an algorithm that will run faster on a quantum computer than on a classical computer. And this is the so-called quantum advantage, where to use quantum computing has an advantage with respect to classical computing. So quantum computing developed quite fast in the 80s and 90s, especially when it comes to the theoretical computer science part and the development of algorithms before actually having the technology. In 1993, Vazirani and Bastrein described an algorithm that showed a clear quantum classical separation, and most importantly, describe a quantum version of the Fourier transform that is an important building block for computation. This is also a critical component for other quantum algorithms, for instance, for factoring large numbers and many other quantum computer applications. So in this course also we're going to study how to develop Fourier transform on a quantum computer, and we're going to look at this original work by Vazirani and Bernstein. Probably the most famous algorithm when it comes to quantum computing is the Shor algorithm. And what is this algorithm? Well, it's the algorithm for factoring large numbers into prime factors. So this is a problem that is believed to be intractable on classical computers, and most importantly is at the core of a public key cryptography as implemented in the RSA algorithm. So to be able to solve this problem with a quantum computer in a treatable way also would allow to have a very strong implication when it comes to cryptography. So the Shor algorithms is this algorithm that allow us to factor in large numbers in two primes factor numbers. One thing that Shor showed is that quantum computing can solve an equivalent problem to factoring large numbers. That is, this equivalent problem is a period finding of a function. Also, we'll see that is rely on quantum Fourier transform. So we are going to be quite quick, but later on in the last module of the course we will spend a little bit more time on the Shor algorithm. So the Shor algorithm is dates back to 1994 when Peter Shor was working at Bell's labs. Looking at the application of quantum computing classical scientific problem, probably the most famous algorithm for solving linear solving using a quantum computer is the so-called HHL algorithm, where HL stands for the last names of the people who invented the algorithm. So Aram Harrow, Avnitanan Hasidim, and Seth Lloyd. So this is an algorithm that has been designed for solving linear system. And this algorithm estimates the results of a scalar measurement of the solution vector to a linear system of equation. So why this algorithm is important? Well, not only allow us to look at how to solve a linear system, but also open up the possibility of developing algorithms that are based on HHL in the area of quantum machine learning. We also see the rise of algorithms that are for data analysis, data analytics based on machine learning. Going to our days in 2014, the variational quantum eigensolver are actually introduced. So these variational quantum solvers are inherently hybrid schemes where the quantum part is important, but also the classical part. So these are algorithms that are executing in large part on a classical system and on a quantum computer. Typically, for instance, is the cost function of an optimization problem is solved on the quantum computing. This is the last slides. So you probably heard about the NISQ era, that is the current period. In 2018, Preskill from Caltech introduced the term NISQ, that stands for Noisy Intermediate Scale Quantum. So this is an influential paper that describes all the system, the current system that can be usable in the near range. This is the last slides of this lecture, and talk to you soon.